Okie doke. Second video on, let me see, the Workhorse macroeconomic model of natural resource use and pollution. So we just looked at the limits to growth, and we said that, I think, economists were super critical, people like Solow, Stiglitz, etc., very famous macroeconomists of the time, were super critical because they were saying that, look, this isn't including all the economic mechanisms of adaptation to resource scarcity. So what did they come up with instead? We're going to have a look at that. What they came up with ended up being called by many the DHSS model. And here are some links to the original papers. There was a special issue of Restud, which was where the main sort of foundational papers were. And they were building on the classic paper by Hoteling from 1931, which was just basically about natural resource pricing or non-renewable resource pricing. Okay, so where were they coming from with this? Very briefly, we can start by thinking about cake. They combined like a cake eating model with the famous Solow growth model. So here's a cake eating problem. How do we set this up mathematically and solve this? Okay, you should be comfortable doing this kind of thing. This is super straightforward. Okay, so you have a think about this. You might want to pause the video. Of course, we set up something like this, right? We're trying to maximize this person's utility, which is the integral over infinite time, assuming the person's infinitely lived, of the utility of their consumption of the cake, discounted at a constant rate. This is the standard formulation. And the cake, that should be S0 there. Sorry, I'm going to pause this. Alright, the initial size of the cake is S0, and the integral of all the future consumption of the cake must be less than or equal to that initial size. And as you can see, there's no depreciation of this cake. In reality, you might think there'd be some discrete depreciation after a week or two when it goes moldy and you can't eat it anymore. But this cake lasts forever. Okay, so let's see what we've got. Yeah, so how do we solve this? I'm not going to spend a lot of time in these videos doing math, or that's not my plan, but I'm just going to take you through this very quickly just to remind you, to get you warmed up on dynamic optimization. You need to be able to do this. Okay, so let's see if this works. I'm going to kill that window and we're going to go over to the paper here. So what have we got? We've got U is integral between 0 and infinity of U of Ct. Oh, we got an extra, right, e to the minus rho t dt. I'm going to use subscripts instead of brackets for my t's, and then we've got that limit on total extraction. Okay, and of course we know that S dot, the change in the remaining stock, is just minus Ct, right? So the stock goes down at the rate at which we eat the cake. Okay, pretty straightforward. How do we solve this? We set up the Hamiltonian, right? So H, and I like, what do you call these? I like the standard Hamiltonians. What do you call that? Current value Hamiltonian, for whatever reason. Most economists use the present value Hamiltonian, right? Yeah, I think, but I just go with the standard. So then the Hamiltonian is H is e to the minus rho t times U of Ct minus lambda ct, and then we take the first order conditions. First one, DHDC should be naught, which tells us that lambda equals to the minus sign, we shifted things across, the differential of this, which is, of course, with respect to c, it's just e to the minus rho t u prime ct. Okay, and then the other condition is that minus lambda dot is the differential with respect to the state variable. The state variable is nowhere to be seen here, so that's just 0. Okay, so we've got an equation in lambda, we've got an equation in lambda dot. We can just differentiate this to get two equations in lambda dot, and then we're going to be well on the way. So if we differentiate this with respect to time, what do we get? We get that lambda dot is, so we first differentiate this bit, then this bit. Okay, so it's minus rho times what we started with, which is lambda. So that's minus rho lambda, and then differentiating this with respect to time is du prime dct by dct times dct by dt. Okay, du prime so this bit is u double prime ct times ct dot. Okay, and then we've got this as well. So in the end we end up with the original expression, which is lambda times u double prime divided by u prime times c dot. So it's plus lambda u double prime ct over u prime ct times dct by dt. Okie doke. But we know that lambda dot is naught, so we've got that. And then if we just skip that, so I save writing out an extra line, then we can cancel these lambdas, and we've got our solution. Because rearrange this, and we end up with c dot over c equals, take the rho over rho, u prime ct over u double prime ct. Right? Yep. All good. If we define, for instance, u of ct is log ct, then u prime is 1 over ct, u double prime is minus 1 over ct squared, and we end up with c dot over c is minus rho. Oh wait, no, sorry. I was thinking something's gone wrong here, hasn't it? This was wrong here. C dot is rho u prime over u double prime. C dot over c is this times 1 over c. And then this comes out right. So what's that telling us? It's telling us that the rate at which we consume the cake declines according to the discount rate. So the more impatient we are, the steeper the decline in the rate of consumption of cake. And then, of course, we have to bring in the transversality condition, because the total consumption of cake So we're going to decline, our consumption of cake is going to decline like this, right? And the bigger row is, the steeper the decline. But then transversality tells us, of course, that this area should be exactly equal to S naught, because we don't want any cake left at the end in infinite time. It has to asymptotically all get used up. And of course, if we're super impatient, we start with a higher consumption initially and then decline more steeply. If we're very patient, our consumption path will be lower initially but flatter. We'll get to consume more later. Okay, so that was a bit of math. Cake eating. Let's see how we're doing for time. Okay, we're up to 10 minutes. I think I'll... So that's just the solution that I did in MATLAB. Let's see. Yeah, I think we'll look at this one as well, and then I'll stop this video. So what's going on here? Oh, sorry, I got to bring that window back. Yeah. So there's the solution to the cake eating problem in MATLAB. What about the capital accumulation problem? Well, this is basically a neoclassical model. We've got households supplying labor to the final goods sector. There's one product being produced. Some of it gets saved as capital, some of it goes to consumption. And the problem is, how much do we save? In Solo, we have a simple saving rule. In the Ramsey or the Ramsey-Cass-Koopmans, we have a rule based, we actually sort of maximize utility, and depending on how much there is here and what productivity is, we decide how much to save and how much to consume, right? So how do we set this up mathematically and solve? Again, this is the kind of thing you should be able to do after a bit of thought. Here we have it. This is the neoclassical growth model, right? Again, we want to maximize utility. That's the same, I think, or I've got a big C now instead of a small one, but whatever. But now we have a production function of capital and labor, and we have this capital accumulation equation. Investment is Y minus C, that's what's left over to go here, and this is depreciation. So that's the neoclassical growth model, which you've all gone through in Macro 1, so we're not going to go through it. But I'll show you something I prepared earlier. This is also from MATLAB, with running the model with some parameter values. This is the phase diagram, and what I'm doing here is starting, so that's just the straight phase diagram. Here I'm starting the economy off with very little capital, and then saying, what does the dynamic rule that we got from the first order conditions? So it's like, here we have this dynamic rule, right? But then we need the transversality condition to tell us how much to consume at the start, given this rule, because we have to exactly use up the stock in infinite time. Okay. Similarly, here in the neoclassical model, we get a dynamic rule, but we still don't know how much to consume at the start. And here we start with very little capital, and depending on how much we consume at the start, the dynamic rule will take us to different places, here or here. If we start off with a lot of capital, again, we can end up in different places. And then transversality tells us that if we end up here, it's not feasible. If we end up here, it makes no sense. We should choose initial consumption on this line, so we end up here. Okay. So that is very quick run through of the neoclassical growth model and a bit about how we solve it. And so what happens, so here I've assumed that we started off with a bit short on capital, and then over time we accumulate more capital and gradually consume more. Okay, so remember, in the cake eating we started off with lots of cake and we gradually consume less because we're impatient. In the neoclassical model, I've started it off deliberately short on capital, so then we build up our capital stock and build up our consumption over time in this case. Right, how am I doing for time? Yeah, I'm out of time pretty much. So with cake, flows of both consumption gradually decline. So what happens in the market economy? Well, basically, as long as there's property rights and so on, then the market economy is going to be exactly the same as the socially planned economy. What happens to the price of cake, which we could work out in a market economy? That rises at the interest rate, at that discount rate, rho. Okay, and that comes from hoteling. Yeah, we'll probably we'll come back to that. Well, I'm not going to go through that, I don't think, in the lectures. We can talk about that. I'm not going to go through it in the videos, but we'll come back to it. The price of cake rises at the discount rate. Basically, if it didn't, yeah, it has. No, I'm not going to talk you through that right now. On the capital and production model, the neoclassical model, quantity of capital approaches its steady state level, consumption follows a broadly similar path to capital. In a market economy, again, if there's property rights and so on, there's no market failures, it's going to be exactly the same. That is the fundamental theorems of welfare economics. How fast does the transition go? It turns out, if you actually sort of parameterize this with reasonable numbers, it goes pretty quick. So here we start off with very short of capital, consumption is only 50% of its normal level, capital is much less than that, and within 20 years we're pretty much at the steady state level. Okay. What happens if there's technological progress? Basically, this whole line just tilts upwards, the capital growth line, the consumption growth line. If you have exogenous technological progress, everything tilts up, but the analysis stays pretty much the same. And I'm going to stop the video there, and the next one will combine cake and capital.